So these first couple, remember we talked about benchmarks and finding percents. So we're going to start out looking at 5,100. What would 10% of 5,100 be? Remember, 510. Very good. Remember, we just moved the decimal point over one spot. Well, 21% is going to be 2 tens and a 1. So the second 10 is also 510. What's 1% of 5,100? Just 51. If I add that up, I get 1,071 is 20% of 5,100. How many of you had that? Good deal. Now looking at 49% of 3,400. This one I'll look at just a little bit differently. 50% is half, of course. What's 50% of 3,400? 1,700. From that, to get to 49, we have to subtract 1%. What's 1%? 34. So 1,700 minus 34 is 1,666. Anybody get that one? Good deal. What's that? Oh, sure. Down here then, converting a fraction into a decimal. My instructions are a little rough there, but if it repeats, show it repeating, otherwise round it to the nearest thousandth. So like 5/11ths. How do I convert 5/11ths into a decimal? Yeah, we do 5 divided by 11. If you were to add the zeros and divide that out, you get 0.454. Do you stop there and round it? No, if you kept going, it'd be 4545. So how would I express that? 0.45 with the line over them, just like that. Perfect. How about 1/6? Well, that's 1 divided by 6. And if I divide that out, if I put my decimal point in and add my zeros, I get 0.16666. What am I going to do with that? Okay, 0.16 with a line above just the 6, because the 1 doesn't repeat, the 6 does. What'd you get for 7/9? 0.7777, or just 0.7 with a bar over the 7. Now 26 4/95 I did intentionally. Did anybody get an answer for that one? Perfect. 0.527272727. So it's the bar over the 2 and the 7. The 5 does not repeat, but the 2 and the 7 do keep repeating. Any questions? By the way, I do not have 261 over 495 memorized. There is a way you can take a repeating pattern and turn it into a fraction, and I'm going to show you that right now. You will not be tested on this, just so you know, but it is something that comes in handy. 0.8, repeating like that. The strategy for turning that into a fraction, all repeating decimals, no matter how complicated they are, can be expressed as a fraction. So what I'm going to do is this. I'm going to let x equal 0.8 repeating. Now there's 2 questions I have to ask to change this. One is, are there any non-repeating decimals? In this case, are there any decimal places that don't repeat? No. So we'll come back to that question in an example where it's relevant. 2 is, how many digits repeat? So in this case, how many digits repeat? Just one. It's just an 8, and it's 8. So because there's only one digit that repeats, I'm going to do this. I want to multiply both sides of that by 10. Why 10? Well, when we were dividing decimals, if I wanted to move the decimal point one place, I multiplied by 10. Multiplying by 10 is because there's only one decimal place. So x times 10 is 10x. What is 0.8 repeating times 10? Well, it's 8.8 repeating, right? It just moves the decimal point over one spot. You think of that as 0.8888. When I multiply by 10, just moves the decimal point over one spot. So it's 8.888888. Now here's where we're going to muddy things up a little bit. Remember, one of the things we can do to an equation is we can subtract the same thing from both sides, right? I could subtract 0.8 repeating from this side as long as I subtracted 0.8 repeating from this side, correct? Right? Well, they do the exact same thing to both sides. But there's a little trick in math that we can use. If two things are equivalent to each other, you can replace them with that. We looked at this before. When we solved an equation, we get x equals 7 or whatever. We can put 7, we can replace the x with 7, and it should check out. But what I'm going to do here is I'm going to replace the 0.8 repeating with x, because x is equal to 0.8 repeating. So on this side, I'm going to subtract the 0.8 repeating. On this side, I'm going to subtract x. And I can do that because x is equal to 0.8 repeating. They're the same value. So I am subtracting the same thing, just in a different form, a different appearance. So on this side, 10x minus x is 9x. Over on this side, well, the 0.8s all cancel out, right? The 0.8 repeating all subtracts out, and all that's left is the 8. So now to solve for x, what do I have to do here? Divide by 9. So the 9 is gone. X is equal to 8/9. X is also equal to 0.8 repeating. So 8/9 is equal to 0.8 repeating. So what we're really doing here, what step one is, are there any non-repeating decimals? What that's about is getting the repeating part, so that's all that's after the decimal point. And then step two, how many digits repeat, and multiplying by the appropriate number, that's getting rid of the repeating decimal so that we have a whole number there. Let's do another example. Now, I have no idea what fraction this is going to come out to be. Well, let's say we have 0.72 repeating, like that. So x equals 0.72, and the repeating is over the 2. Now, our first question was, are there any decimals that don't repeat? Yeah, there's a 7 here. So because there's one decimal place that doesn't repeat, I have to move that over. So I'm going to do this. If I multiply by 10, I get 10x is equal to 7.2 repeating. It just moves the decimal point over a spot when I multiplied by 10. Does that make sense? I just multiplied by 10 on both sides. Does that make any sense? Kind of? Okay, so the reason I did that is I want to get it so that all that's after the decimal point is the repeating portion. Okay? So now, question 2, how many digits repeat here? Just 1, right? So now I'm going to move it over one more spot. To do that, I multiply by 10 again. Well, 10x times 10 is 100x. 7.222222 times 10 is 72.22222. 72.2 repeating. So the reason I did this first step up here, to get the repeating part, so that the repeating part was all that was after the decimal point, because I'm trying to get rid of the repeating portion. So in order to get rid of it, I've got to isolate it. So it's all that's after the decimal point. So now this is the part where that repeating portion is by itself after the decimal point. That's what I'm going to subtract by. So I'm going to subtract 7.2 repeating. And notice what that does is the 0.2s that repeat are all going to cancel out. They're going to be gone. What do you think I'm going to subtract over on this side? I'm not going to subtract 7.2 repeating. I'm going to subtract 10x is equal to that part, right? So down here, 100x minus 10x is 90x. 72, the 0.2 repeating is gone. That all canceled out. So it's just 72 minus 7 is 65. To get x by itself, I divide by 90. So x is 65 over 90, both of which can be reduced by 5. So x is 13 over 18. So 13/18 is 0.72 with the 2 repeating. So let's get wild and try one that's really weird. This you won't be tested on, no. Maybe an extra credit question. Or 2. Or 5. If you have some of the steps right, I will give you some of the points. Okay, so looking at this here. First question, are there any digits that don't repeat? Any decimal places that don't repeat? There's 2 of them, the 3/8, right? So if x is equal to the 0.38 and then 147 repeating, what do I have to do to isolate the repeating portion? What do I have to multiply by? 100. Very good. Times 100. Because that decimal point's got to move over 2 spots. So now I have 100x equals 38.147. I have the repeating portion isolated after the decimal point. That's all that's after the decimal point. Now my second question, how many digits repeat? 3. So that means I have to multiply by 1,000 for 3 digits. You got it. So now 100x times 1,000x is 100,000x. Here the 1,000 moves the decimal point over 3 spots. This is 38,147.147 repeating. Because that 0.147 just keeps going. I can move the decimal point over as far as I want to, and it's still going to be going back there repeating. What are we going to subtract from this? Well, I go back up to that step. That's what I subtract. I subtract 100x here and 38.147 repeating over here. So 100,000 minus 100 is 99,900x. Over here, the 0.147 repeating cancels out. 38,147 minus 38 is 38,109. And then I'm going to get x by itself by dividing by 99,900. So x is 38,109 divided by 99,900. Can that be reduced? Well, the 99,000 is even. I can divide by 5, 2, or 10, right? Can I divide by any of those with the 38,109? No. But what can the 38,109 be divided by? If I add up the digits, 3 plus 8 is 11, plus 1 is 12, plus 0 is 12, plus 9 is 21. It's divisible by 3. 999 adds up to 27. That's divisible by 3. So we can divide each of those by 3. So this is what? 1, 2, 703. This is 333. I think that's as far as we can go with that. So 12,703 over 33,300. What do you think? A lot of fun? Try that one in your notes. See if you can make it work. Okay, so we're going to let x, of course, equal the 0.283 with the 83 repeating. What are we going to do from there? Times 10, because there's one digit that doesn't repeat. So 10x equals 2.83 with the 83 repeating. Then what? Times 100. Why 100? Because there's two digits that do repeat. So 10 times 100 is 1,000x. 2 times 0.83 repeating is 283.83 repeating. Then what? We're going to subtract this one up here. So subtract 10x. And over here what we're subtracting is 2.83 repeating. So 1,000 minus 10 is 990x. Now the 0.83 repeatings all cancel out, subtract out. 283 minus 2 is 281. And then divide by 990. X equals 281 over 990. Can that be reduced? No, it cannot. Okay. Anybody have that one right? A couple of you? That's not too bad. It's more than usually the first time I let you try one of those on your own, it's kind of baffling. So good. Now I promised you guys last class that at some point I would show you how your calculator converts between fractions and decimals. Most of your calculators have a button that looks like that. F to D key, it's called. Fraction to decimal. It is generally a second function, which means it's printed on the calculator above one of the other keys. My calculator on screen here does not have one, so I'm kind of out of luck. But your simpler ones do. Biggest advantage of the graphing calculator, by the way, is most graphing calculators suck at doing fractions. So, on the smaller calculators, is there anything, is anybody that did not find the FD key, the fraction to decimal key? All right. So the way you would make that work, let's say you enter 0.48. You usually have to hit equals or the enter key to put it in first. Then you have to usually hit second or shift, depending on your calculator, and that FD key. And then hit enter again or equals again, and it should change it to a fraction. Did it do it? Changed it into 12/25ths. Now, sometimes it'll stumble a little bit going from decimal to fraction. Most of your calculators have a digit limit. Some of them have a 3-digit limit within the fractions. So that means if you have a denominator of bigger than 999, it won't convert it. Others, if you have the 2-line display, have a 4-digit limit. So it won't display any denominator over 9,999. So both of those styles should have been okay with this problem. Going the other way is easier. Couldn't get it to work? No? Okay, I'll stop over in a second. Going the other way is a whole lot easier. You use the ABC key to enter a fraction. So let's say you're going to put in 27/53. You type in 27, do the ABC key, 53, hit equals again to enter it into the calculator, and then shift or second and that FD key. Now, depending on the calculator you have, all of your scientific calculators, every key has 2 functions. Some of your scientific calculators, every key has 3 functions. You have a second key and a third key. Or does this one have a third key? No, this is just a second and an alpha key. Okay, so that is how your calculator will automatically go from fraction to decimal for you on some of the simpler ones. Now, the one we just did up here, the 281 over 990. Go ahead and enter that in. 281, ABC, 990. Hit equals, and then go the other direction. You get the point 2838383. Perfect. Hit the shift and the FD again and see if it turns it back into a fraction. The only problem is there's no way to enter the repeating decimal on your calculator. So you can't put in the repeating decimal and get the calculator to automatically change to a fraction for you, because there's no way to tell the calculator what digits repeat. If you have a math type calculator, and there is a TI-30 math type version out there, that actually does have that function, but that calculator is really difficult. It's kind of a pain to work for the simple stuff, because you got to go through a lot of extra keystrokes. So. Okay, enough calculator fun. We left off yesterday dealing with percents. So let's go back to talking about percents. And we left off, we had converted percents to decimals and to fractions, and the other way around, decimals and fractions back to percents. Some of the trickier ones we found is if we had something like this. Oh, let's see, what do I want to do here? $473 1/3%. Convert that into a fraction. And just for a review, I'm going to let you try that one in your notes for a minute. So the first thing I would do on this, it's over 100%. So the 4 for the 400 is just going to be a whole number in front of whatever this fraction turns out to be. So the only part I really have to convert is the 73 1/3. Now I could have done 473 1/3 over 100 and then pulled out the 4 100s so that it's 4 and 73 1/3 over 100. You're going to get me the same spot. So the real trick is to take this part here, 73 1/3 over 100, and get it converted into a fraction. That was get rid of the fraction within the fraction. 2 ways I could do this. We did 73 1/3 divided by 100, or we just eliminated the denominator of our fraction that's within the fraction. And how would we do that here? We could multiply by 3 on top and bottom, numerator and denominator. Why did I pick 3? Because my denominator here is 3. So multiplying by 3 will get rid of that fraction. 73 1/3 times 3 is 220. I'll let you guys confirm that on your own. You can do 73 times 3 is 219 plus 1 is 220 over 3 times 3 over 1 gives you 220. 100 times 3 is 300. Both of those may be reduced by 20, giving me 11 over 15. So this is 4 and 11/15. What do you think? Did anybody come up with 4 and 11/15? How many of you would have got there if I had given you a few more minutes? How many want to run from the room crying? A little bit, just on general principle, not just from that problem. I have that effect on people. Okay, so 4 and 11/15 is the answer. Let's do one more of those since they seem to be a little difficult. Let's see here. Let's do 268 and 1/3%. Convert that into a fraction. Talk me through it. What's that? Okay, I can pull the 2 aside since that's over 100%. So it's going to be 2 with some fraction. Then what? 68 and 1/3 over 100. Okay. And then, oops, I'll make that actually look like a 0. Times 3. Why 3? My denominator is 3. No, they're not always going to be 3. I just tend to do that because there's some patterns where 1/3 are really easy to convert into neat fractions. So, what do I get on top? 68 and 1/3 times 3. 205 over 300. Very good. Then what? Simplify. Divide by 5 gives me 41 over 60. So 2 and 41/60ths. How many of you got that? Cool. So we can convert our percent into decimals and fractions. Getting to be a lot easier. Okay, so our next step to actually calculate with these. When we were converting fractions back into percents, remember if we were given something like 5/16 and we wanted to convert that into a percent, we read that as 5 out of 16. And a percent is always out of what? 100. And we talked about these proportions before, where we have 2 ratios, or 2 fractions if you want, that are equal to each other. And if we have one of the numbers missing in one of those ratios, how do we find it? Cross multiply. 5 times 100 is 500. And now technically what we're going to do is we're going to do 16 times this missing number has to equal that. But the shortcut is we can just divide by the 16. 500 divided by 16 is 31.25. So 31.25 out of 100 is 31.25%. This same proportion is going to do pretty much all of our calculations with percents. So we're going to start out here in the first hour dealing with simple percent calculations. So let's say I told you, or asked you to find 30% of 70. I'm going to set up a proportion where there's one ratio equal to another ratio, or one fraction equal to another fraction, if you want to think of it that way. In a percent problem, the one ratio that I know it's easiest to find is the percent itself. In this case, the percent is 30%. What is that? What ratio does that give me? 30 out of 100. 30 to 100. 30 out of 100. Now there's always 2 other numbers. There's always a number that represents the piece that we are interested in. And another number that represents the whole amount, or a starting value, initial value, initial amount. When you're looking at this 30 over 100, the 30%, The 30 is representing a piece of a whole amount. And the 100 is representing the whole amount. You can actually think of that 100 as being 100%. 100% is everything, the full amount that the whole problem is based on. That doesn't mean you can't get more than that. You can't get larger than that. It just means that's what everything is based on. That's what everything started with. Everything else builds from that. So in this case, we have the 70, and we have to decide, does that 70 go with the 30? Is it representing the piece that we're interested in? Or is it the whole amount? Does it go with the 100? And in this type of problem, whenever you see that word of, you have to ask yourself, does that really mean out of? In this case, yeah. Find 30% out of 70 is what that really means. So what does that imply about where the 70 goes over here? On the bottom. We want to find a number out of 70. So now to find that missing number, we cross multiply. 30 times 70 is 2100. Then we divide by the 100 is 21. So 21 is 30% out of 70. So in this problem, again, I'm given a percent. I'm going to set up this proportion. One ratio equals another. I'm going to start with the percent. What is it? 180%. So I'm going to write that as 180 over 100. Now this should ring some bells right away. Throw up some flags. 180%, of course, is larger than 100. So we're going to deal with an ending amount or a piece that we're interested in that's larger than the base amount or the whole amount. When you're looking at this, the wording in many cases helps you figure out where stuff goes. Blank is 180%. The blank matches up with the 180. The blank is the 180. And again, of 40 can be thought of as out of 40. So the 40 once again goes on bottom. From there, what do? Well, 180 times 40 is 7,200. Divided by 100 is 72. So 72 is 180% of 40. I worded this one quite different, but falls along the exact same lines. In my proportion, where am I going to start? 75% is 75 over 100. Now the wording is very different. All the other ones, it's been something before the 75% and then only one thing after. Here, both of the other numbers come after. Both the number we have, which is the 80, and the missing number, which is our blank. So what I'm going to do is I'm going to cover one of them up and see what it says. If I cover up the missing number here, we get 75% of 80. Well, 75% out of 80 is how I would read that. That seems to indicate that the 80 is going to go on bottom. Let's look at it with the other number, the 80 covered up. Cover up the of 80. Sorry. Allergies are kicking me in the tail today. So 75% is blank. Implies that blank goes with the 75. So that blank goes here. So yes, that does reaffirm that the 80 has to go on bottom. And now we will cross multiply. 75 times 80 is 6,000. Divided by 100 is 60. 75% of 80 is 60. Any questions so far? You do the 0.75, yeah. We'll look at that in just a minute. So let's say we have 42 is blank percent of 70. I told you before that we always start with the percent. But here we don't have a percent. Well, that doesn't change anything. We're still going to start with the percent. Instead of a number over 100, though, it's just blank over 100 because we don't know what the number is. But we do know that whatever that percent is, it's going to be out of 100. So now we have two other numbers here. We have the 42 and we have the 70. One of them matches up with our missing piece, the missing percent. And the other one matches up with that whole amount or that original amount. Well, if you just look at the wording here again, 42 is blank percent. What does that imply about the 42? It goes on top. It matches up with our missing percent. Of 70, again, if you read that as out of 70, 70 goes on bottom. Then you cross multiply. Now, you're still going to cross multiply and divide. It's just there's a different number missing in the proportion. So you're going to cross multiply in a different direction. 100 times 42 is 4,200. Divided by 70 is 60. 60 out of 100 or 60%. 42 is 60% of 70. Now, for many of you, you may have had a teacher somewhere along the way that taught you is over of. Any of you hear that? With percents?
Yeah, I always forget which one goes for which.
Okay. You know, in most of these base problems like this one, where it's just a simple number sentence, that does work out pretty well. The is goes on top, the of on bottom, and then the other fraction is your percent. Your number over 100. The problem is when you get into word problems, more complex word problems, the is and the of are not always used the same way. That only applies to base number sentences like this. And it does, you can see if you go back through all the problems we've done, the number that goes on top is next to the is. Either the is right before it or right after it. And the one that goes on bottom, again, of is either right before it or right after it. I don't like to preach that because that's teaching you to use a crutch on the words rather than actually understanding what's going on. But it is definitely about matching up the pieces. Any proportion is. That whatever is on top here has to represent the same thing as what's on top here. It's just different ways of representing the same thing. So they have to be linked together. So if I give you blank percent of 90 is 18. Where would I start this problem? Well, we always start with the percent. Do I have the percent here? No. So what do? Blank over 100. Perfect. Then what? Okay, over here, 18 over 90. Now, off what I just said, of course, you see the is between the 90 and 18. So which one does it go with? Well, the of is by the 90, so the of has to go with the 90. But again, I would look at it like this. Blank percent out of 90 implies the 90 goes on bottom. Blank percent is 18 implies the 18 matches up with that blank, the missing percent. So now again, we're going to cross multiply and divide. 100 times 18 is 1800. Divided by the 90 is 20. So 20 out of 100 is 20%. 20% of 90 is 18. Any questions so far? Okay. Try this one in your notes for me quick. Yeah, sorry. There you go. So blank over 100. Come on. Equals what goes on the other side? 27 over 30. Cross multiply and divide, we get 90. Very good. How many got 90%? Oh, clean sweep. Good deal. That would be a nice dream, wouldn't it? This one, once again, is slightly different. But my percent is back, which makes us feel a little bit better. Where do we start? 70% is 70 over 100. Where does the 63 go? On top. 63 is 70%. So it implies the 63 matches up with the 70. So now once again, there's a different piece of the proportion missing. But the calculation is still the same, cross, multiply, and divide. Sometimes we go in a different direction with our cross multiplying, but it's always the two numbers that are diagonal from each other. So 100 times 63 is 6,300. Divide by the 70 is 90. So 63 is 70% of 90. So if I give you blank percent of 80 is 32, how do I set that one up? Blank over 100. 32 over 80, good. Cross multiply. 100 times 32 is 3,200. Divide by 80 is 40. We get 40%. If I give you 15% of blank is 9, how do I set that one up? $15 over 100, I have the percent again in this one. That is 9, implies the 9 goes on top. Out of blank implies the missing number goes on bottom. So 100 times 9 is 900. Divided by 15 is 60. So 15% of 60 is 9. How are you guys feeling so far? Anybody have major questions on setting up these proportions? Now, you mentioned, can't I just turn it into a decimal and multiply? Well, yes. What you're referring to there, and I'm going to scroll back up. You notice I left the right side of my paper empty on all these. What you're referring to there is something called the rate method for percents. And what the rate method says is you can solve these by turning the percent into a decimal. So here in this first one, the percent is 30%. What's that going to be as a decimal? 0.3. And what I do with the decimal in this problem is I take my other number, the 70, and I multiply by 0.3 to get 21. Is that the answer? Yep, that's what I got with the proportion. So if I look at this one, 180% becomes what as a decimal? 1.8. So I'm going to take my other number, the 40 here, and multiply by 1.8 to get 72, which is the correct answer. If I take that base amount and simply multiply it by my percent as a decimal, it comes out the correct answer. Now, if you look at these problems, it makes sense. I am taking this base amount of 70 times 30 and then dividing by 100. Well, it's just the 30 over 100 is just my decimal version of the percent. So this example here, 75% is what is a decimal? 0.75, yeah. And then 80 times that is 60. So why don't, that seems pretty simple. I turn it into a decimal, I multiply, and I've got my answer. Well, because that isn't always the way it works out. I'm going to go down here to this one here. I have my 70%, which is 0.7 as a decimal. But am I going to take 63 and multiply by 0.7? No, because the 63 does not represent that whole amount or that base amount. The base amount was multiplied by 0.7. Here, the 63 is representing the portion or the piece that we are interested in. So in this case, I would have to take the 63 divided by 0.7 to get the 90, which is my desired answer. So the problem with, the reason I like the proportion that we were doing here to begin with is because all you've got to do is figure out where the numbers go. And once the numbers are in there, the calculation is always cross multiply and divide. So it's always the same calculation. You just got to locate the numbers. The percent is pretty easy. The percent always goes percent over 100. It's the other two numbers that you have to get in the correct place. And again, as you get used to it, you learn to see that connection between the percent and the number and the 100 in the number. In the rate method, however, you change that percent to a decimal, which isn't too hard. But then you have to remember, do I multiply by that or do I divide by that? Like in this one here, I've got my 15%, which is 0.15 as a decimal. Is it going to be 9 times that or 9 divided by that? Divided by that. Very good. Yeah. And if you have that memorized, that's fine. It works. How about one like this, however, where I'm missing the percent? There is no percent to move the decimal point in, to turn into a decimal. Well, here you do the is divided by the of, if you want to use that term, or, sorry, the piece of interest divided by the whole thing, or the initial amount, gives you 0.4. So now you divide and you get the decimal, and now you have to change the decimal into a percent of 40%. That was the way I was taught. The rate method is how I was taught, and that's actually how I do when I'm doing percents in my head. I still do it that way. But I have it memorized, and I can flip through it. I've found that if you're just starting out with percents, or if you struggle with percents, you make a lot fewer mistakes using the proportion. When we get into word problems, the proportion has definite advantages that I'm going to show you in just a few moments. If you were taught the rate method and you like doing it and you're good at it, feel free to keep using it. In fact, there are a couple of applications of percents. There are tons of applications of percents. Like I mentioned yesterday, percents are one of the most powerful tools in math. Ratio and proportion, I think, is the single most powerful tool in math. Percents would probably come in really close to being the second most powerful tool in math. So they're a very powerful tool. There's all sorts of applications for them. There are a number of applications for percents for using the rate method is simpler because you're always going to be going from a whole amount to finding a piece of interest. And as long as you're doing that, then that rate is simple to use. And it'll show you that application. But those are some of those applications. Those applications tend to be spots where it's a very simple formula to do a quick calculation over and over again. Let's look at some word problems. So let's say that you work as a quality control in a manufacturing setting. And your experience is 2% of parts are defective. So on a day where 92 parts are found to be defective, estimate how many parts were produced. So you might be looking at this saying, I don't know a whole lot about quality control. Well, you don't. You don't need to. All you need to understand is how percents work. And whenever you see a percent in the problem, it should indicate to you that you're going to use some sort of proportion like this. Now, you'll notice I left a lot of space around my equal sign. That's because I'm going to make some notes around my equal sign here as I put in the numbers. Now, we have the 2%. 2%, of course, represents 2 out of 100. So the question is, what does that 2 really represent here? When we have a percent, there's always at least 2 amounts. Sometimes there's 3 amounts being represented. In this case, the 2 amounts that are in the problem are defective parts and total parts produced. Yeah. One of those numbers is usually a total amount. So what does the 2% represent? Well, what it represents is the defective parts. 2% is the defective parts. The 100 represents, as always, the total parts. So now when we're looking at this, the 92, does that represent total parts produced or does that represent defective parts? Defective parts. So where does that go in my proportion? It has to go on top because it's got to go with the defective parts. Both the 2 and the 92 represent defective parts. So we are looking for the total parts produced. That is the second thing. A lot of people, they get 3 out of the 4 numbers in a proportion and they just want to cross multiply and divide and there's their answer. You have to stop here and ask yourself, does this piece of this ratio here represent what I'm trying to find? It represents the total parts produced. Is that what I'm trying to find here? Yes, it does. So I can cross multiply and divide. 100 times 92 divided by 2 is 4,600. There were 4,600 parts total produced that day. Now you might be thinking, that's kind of silly that I had to ask, is this what I'm really looking for? I mean, what else could it be? Well, let's look at this. Similar problem, still dealing with quality control. So 3.5% of parts are defective. I'm going to abbreviate here. So on a day where let's say 154 parts or defective parts were found, how many good parts were produced. So again, we have a proportion of some sort here. And again, you'll see I left a lot of space around my equal sign. I'm going to start out with my percent, 3.5%. That is, of course, 3.5 over 100. Now, just like last time, the 3.5 represents what? Defective parts. The 100 represents total parts. That 100 will always represent either a total or a beginning or initial amount. What other numbers are in the problem? Well, there's the 154. What does that represent? Defective parts. So that has to go on top. What's this missing number in my proportion represent down here? Total parts. Is that what we're looking for? How many good parts were produced? Not total parts, but how many good ones were produced. So what we're going to get there is not what we're looking for. Let's go ahead and find it anyway and see if we can get to the answer from there. So 100 times 154 divided by 3.5 is that 4,400? Is that right? $440? Oops, I divided by something wrong here. 440, so an extra zero. Is it 44? So 100 times 154 divided by 3.5. Yeah, that's 4,400. So that's 4,400 total parts produced. How would we get from that to my defective parts? You got it. Perfect. The 4,400 minus the 154 defective parts, which is 4,246 good parts. Or acceptable parts, whatever term you want to use for it. So you do have to be careful. Sometimes that missing piece in the proportion is not what you are looking for, but it can help you get to what you are looking for. I told you before that when we're dealing with percents, there's usually three things. And this problem represents that very well. When we have that percent, the 3.5%, there's the 3.5 and there's the 100. The 100 always, of course, represents the total. The 3.5 represents that piece of interest that we're interested in. The third part is what's left over. Well, what number represents what's left over? Well, this is 3.5 out of 100. If this is out of 100 and we've used up 3.5, what's left over is the rest. 100 minus 3.5, or 96.5 out of 100, or 96.5%. Every percent has what's called its complement. Complementary percents. Now, when we dealt with angles, complementary angles added up to a right angle, added up to a square corner. When we're talking about percents, the word complement means it adds up to the whole thing. So the complement of a percent is 100 minus that percent. So 96.5 and 3.5 add up to 100, so they are complements. Whenever you see a percent, you need to be aware that it has a complement that is the rest of the whole amount. So in this case, the 3.5% represented the defectives. What we were interested in was the rest of the whole amount, the 96.5%. Often when I do story problems with percents, you can see here in both of these problems, I set up my proportion and I left room in the middle here to label the pieces. I will often actually just set up a table. It looks like this. And on one side of the table you have percents, and on the other side you have the numbers. And in the middle you have the descriptions. The defective is the 3.5. And I have the 100%, which is the total amount. I'm actually going to do this. And I had the 154 over here that represented, that is the number that represented the defectives. This table helps me organize things. Now you notice I left a space here in the middle of my table, because in that space is the rest of the percent, which would be that 96.5. That represents the good parts or acceptable parts. The nice thing about this table here is there are 3 distinct lines, and I can set up a proportion using any 2 out of those 3 lines. One line that I use always has to be the line where I have both numbers. I have that defective, I have both the percent and the number for that item. So I have to use that line because I have both numbers. The second line that I use, and I can use either of the other 2 lines for my second line, but it's quickest if the second line that I use is the one that contains what I'm looking for. And in this case, I am looking for the number of good parts. It contains, this is what I'm looking for, is this value. So the line that contains that is that blue line across there. So I could set up a proportion that looks like this, 3.5 on one side and 154. Notice I'm just replacing the words with the equal sign here. So the 3.5 goes with the 154. On bottom, what goes down there for the good? Do I know the percent side of that? 96.5. Do I know the number side? No, that's what I'm looking for. And if I cross multiply here and divide, what I get is 4,226? 46, there you go. Now, in some cases, this is easier to set up. Somebody may think that's more confusing. The reason I bring that up is there are cases where you have to be able to think like that. You have to think of that complement, because sometimes what is given is not what is represented by the percent. So back to that quality control issue again. So let's say that we have 1.5% defectives. So on a day where let's see here. $3,940 good parts are produced. How many total parts were produced? Well, if I were to jump in to solve this, where does the 1.5 go here? Okay, so if we do that, 1.5 over 100 for a percent. On the other side here, where does the 3940 go? Well, the 1.5 represents the defectives, right? The 100 represents the total. Which one of those is represented by the 3940? Say neither. Neither one of them. The 3940 represents the good parts. So here, the 1.5, it's not useless information, but it's not part of the proportion that we're going to set up. You have to think in terms of complements. If 1.5% are defective, that means what percent are good? Well, 100 minus 1.5 is 98.5% are good. So what I would set up in my proportion is actually 98.5%, or 98.5 over 100. Now the 98.5 represents good parts. The 100 still represents total. And we have 3,940 good parts. Defined, are we looking for this is the total here. Are we looking for the total? Yes, we are. So it's 100 times 3,940 divided by 98.5 gives us 4,000 total parts. This is why I like setting up that table. Because in the table, what I can do is I can use words to describe the problem. So my percents are on one side, my numbers on the other. In the middle here are my words, my descriptions. I know that defective parts plus good parts equals total parts. Correct? Does that make sense? I could switch it around. I could say good parts plus defective parts equals total. I say good plus bad. It doesn't really matter what words I use as long as I understand what they mean, what they stand for. On the percent side, I know the 1.5%. What does that represent? Defective, good, or total? Defective, 1.5%. Do I know anything else on the percent side? There's always one thing I know, even though it's not explicitly written out, and that is the 100. Where does the 100 always go? The total. Total or initial, if we have an initial amount, right? So the 100 goes there. The other number we know is the 3,940. That's going to go on the number side, and it's describing good parts. What are we trying to find? The total parts, right? So since this is the number we're trying to find, that tells us we're going to need this line. We're going to use that because it contains what we're looking for. The other line that we always use is the line that we have both numbers in. Unfortunately, here we don't have any lines where we have both numbers, do we? Can we create a line where we have both numbers? Well, to do that, I'd either have to find this number or this number. Can I find either of those? Yeah, I can find this one here really quickly, can't I? What's that have to be? 98.5. Because this one plus this one has to equal this one. That applies in both columns. This number plus this number has to equal this number. This percent plus this percent has to equal 100%. So now I have this line I can use, which gives me this proportion if I wanted to pull it out. Or I can actually just do the work right in the table if I want to. I'm not going to use this top line, so I'm just going to kind of cross it out. So I'm going to cross multiply. These two numbers are the numbers that are diagonal, so it's going to be 100 times 3,940, which is exactly what I did up here. Then dividing by the 98 gives me my 4,000. Now, I realize that table might be kind of confusing right now because you're just seeing it. But it's a powerful tool to be able to organize stuff in that table. If you can write the problem out in words and then start matching numbers up with the words, the problem falls into place. Now, we're a little late for our break, so let's take our break right now. It is 10:21. Let's come back at 10:31, and we'll continue from there.